Guys, welcome to YouTube channel Foundation JEE. Today's lecture is on sound, which is last lecture of class 9th physics. In this lecture, we will first discuss wave motion and wave. Then we see the definition of sound and how we hear the sound when someone speaks, or you can say when medium of particle vibrates by vibrating object. And then we see one instrument which is used for creating vibration in medium is known as tuning fork. Then guys, we see bell jar experiment by which we discovered whether for propagation of sound medium is required or not. Here we are talking about medium, then we are talking about gaseous, liquid and solid medium. After learning all these things, we will see the characteristic of sound, in which we discuss wavelength, frequency, time period, and at the end of this lecture we will solve two numerical problems for better understanding of sound. Okay, so now we start first with wave motion. Wave motion, guys, when in a space disturbance produced at one place, then without transferring medium of particles, the disturbance moved to another place. Such type of disturbance is called wave motion, and such disturbance itself is called wave. Okay, now we see the definition of sound. Okay, guys, it is kind of vibration produced by source so that medium particle to and fro from its mean position and wave propagates and we hear sound. Guys, first of all, here you understand the meaning of to and fro. Okay, suppose one particle we consider of a medium like sea, air. Okay, now suppose this particle is connected with a thread, then it becomes a pendulum. Okay, now when we apply sound or creating vibration, then this point move like this and coming to this point, again it return back and go to this position. Okay, so this action is happening continuously when source is vibrating continuously. Okay, and this will complete one cycle. See, first the particle is here, again it is going here in this direction, again back and come to this point, again return like this, or this cycle is happening continuously when the source of vibration is continuous. Okay, so what's happen when we speak, then suppose this one is a air particle and this one is also a air particle and like this. Okay, so suppose we speak here, okay, by a speaker. Okay, so what's happened, this particle goes to this point and exert a force and again return back to its original position, then this particle again apply force of this particle and again return back to its original position, or you can say oscillate when we are speaking continuously. Okay, again this one apply a force and again return back to its original position or equilibrium position. Okay, so if you are here, suppose, so you hear the sound. Okay, so you can say after vibration of source stops, the oscillation of medium particles stops and come to their original or equilibrium position. Okay, so you can see this one by an experiment. Here I have made one simple pendulum. Okay, see guys, this one is a simple pendulum. Okay, now this one is suppose a particle. Now we exert a force, then it is come this position, again it to and fro. Okay, means back and forth motion. Okay, so you see when time elapses, then it again come to its original position. This one is its original position or equilibrium position. So such type of motion C is called oscillatory motion. Okay, or guys, you see, suppose a force is applying here, so when it will come here or start counting of a cycle, complete one, then again it come here, then it completed one cycle. See, or what is the time elapsed to complete this one cycle is called its time period. Or see how this work. Again, suppose it is here, I pull it and leave it, then again it come to its position. Guys, one thing you notice, what's happened, the motion of this particle at its equilibrium position is maximum. Okay, or these points here, or you can say here, is known as a extreme points. Okay, now you understand to and fro or back and forth of particle. Now next we will discuss the construction of tuning fork and how it works for creating vibration in medium. Okay, tuning fork. Okay, so this is U shape material and its base is connected by one handle. Okay, so this one is known as a stem and this part is known as prong. So you can say in tuning fork there are two prongs. Okay guys, due to variation of size of prong or stem in market, it is coming for creating different frequency. Okay, so finally we can make a definition. A tuning fork is an instrument for creating vibration in medium, and it is made of elastic metal like steel or aluminum alloy. Guys, alloy means mixture of more than one metal. Okay, so why this tuning fork is elastic? Because suppose this one, okay, when you strike it on rubber pad, okay, so what's happened here, see, its shape becomes like this one, see, again like this one. Okay, so this position is changing, it is coming forward, again it is returning back, again this is creating a cycle, means it is coming forward, then again return back, again coming to this extreme position, again forward. Okay, so suppose guys, here uniform gaseous mixture, or you can say air are present. Okay, so now suppose guys, this tuning fork strike to one rubber pad and we put here, then when it is in forward motion, then air particles accommodated here, again it is come back, then the air particles are moving away. Okay, again suppose here this is in forward motion, again it is returning back here, again this is going forward. Okay, so now like this. Okay, so what you see, the average density of air are not uniform in this medium. Okay, where the crowd of air particles are more is known as a compression region, or where particles are less of medium, then it is rarefaction, then again compression, then rarefaction, then again compression. So when this tuning fork vibrate continuously, then compression, rarefaction, compression, rarefaction, compression, rarefaction, such waves are propagating. Okay, now here see compression, okay, or R is rarefaction. Okay, so when the vibration of this tuning fork stops, again the medium of particle comes to its original position. Okay, now guys, next we see for propagation of sound, medium is required or not. Okay, so when we are talking about the medium guys, we are talking about gaseous, liquid and solid here. Okay, whether propagation of sound medium is required or not. Okay, so we will see this by an experiment which is known as Bell jar experiment. Okay, what this experiment say guys, suppose this one here is a jar. Okay, now the bottom of this jar is connected to a vacuum pump. Okay, now here one electrical bell is connected like this one. Okay, now there is one switch is here. Okay, now the neck of this jar is sealed by cork, which is a sound absorbing material, or it cannot pass the sound through it, so you can say it is an insulating material for sound. Okay, now suppose guys, initially air particles are present here. Okay, or these are wires or connected to power line. Okay guys, when we on the bell, that is making on position of this switch, then what's happen, you will hear the sound. Okay, now next, when we start the vacuum pump, then it will extract the molecule of gas, or you can say air particles, in this jar container. So what's happened, this becomes empty, or you can say there are only few gaseous particles present. Okay, so if all the particles are removed, or it becomes here empty. Okay, now again you on this bell, then you will not hear sound. Okay, so what you see, when the medium particles are removed, then sound is not propagating. Okay, so you can now say, for propagation of sound, medium is required. So such type of wave, here sound wave, is known as mechanical wave. Okay, those waves don't required medium particles for propagating or transfer energy one place to another place in a space is called non mechanical wave. Guys, example, radio waves, it is a kind of electromagnetic wave, or you can say light wave. So see how light waves does not require a medium. Okay, suppose this one is our sun. Okay, now this is emitting here light wave. Okay, now this one is our earth. You know, only the air particles are present surrounding to the earth. Okay, and no particles are present after the surrounding of earth, so we say it is a vacuum medium. So even though from surrounding to this distance no particles are present, however we are getting a light. Okay, so that's why we say light is a non-mechanical wave. Okay guys, so one point you remember, when you extract particle from medium, here we are talking air, then pressure is less compared to surrounding. Here you can say here pressure is low or here pressure is high. Okay, because what you did, you on the vacuum pump or you extracted the air particle or gaseous molecules from this jar. Okay, now guys, next we see the characteristic of sound. Characteristic of sound. Characteristics of sound here. Suppose guys, here air particles are present in normal condition. Okay, like this. Okay, now we put one speaker like this, loud speaker or source of sound. Okay, so what's happen here, when the speaker start making sound, then the air particles are crowded initially at source position and again go away from sound position. So guys, what you see here, the air particles were more in this figure, so this point is known as a compressed region, or here the air particles are less, so it is known as rarefaction region. Then again compressed, rarefaction, compressed, rarefaction, and then this one. Guys, here the density of air is more from average density of air, or this region here density is less compared to average density. Okay, same thing is also applicable for pressure. Okay, so where crowd is more, okay, then pressure is more. Okay, now we show this one by vertical line here. See, so where the pressure is more, then air particles are more, or the here vertical lines we are showing the pressure like this. Here you see, so what you see here, so this one pressure is more compared to average pressure of this air. So this one is compressed region, again rarefaction, compression, rarefaction, compression, rarefaction, and again compression. Okay, so pressure is varying like this. Okay, so average pressure. Okay, so at compression region, density and pressure is more compared to average density and pressure. Okay, so guys, for rarefaction region, density and pressure is less compared to average density and pressure. Okay, so this one is for rarefaction. Okay, so now see, these are speakers for showing the phenomena. This is a loudspeaker or source of sound. This one is also loud speaker or source of sound. Okay, so guys, now when you plot this one on paper by a graph, then what you see here, suppose this one is a normal, or you can say average density and pressure. Okay, or this one axis is distance axis, or now we show variation in density or pressure. Okay, so what you see at source, the air particles are more, then it has a maximum value, then it gradually decreases and come to average, again it go below the average value, the density or pressure, again it start moving up or coming to peak, and again like this. Okay, so you see here, this one is a compressed region. Okay, then again like this one. Okay, so the value of pressure more than here the average value which create a peak here is known as crest. Okay, and in compressed region, guys, in rarefaction region there is one valley. Okay, so here density and pressure is below the normal or average value. Okay, so this one is known as a trough. Okay, so guys, the distance between the two consecutive crests here to here in this graph is known as wavelength of the sound. Okay, so you can say, guys, here wavelength is it is distance between two consecutive crest or trough. Okay, it is represented by symbol lambda or SI unit is meter. Okay, now the second one is time period. Okay, so guys, time period, time taken by density of medium to complete one oscillation in medium is called time period. Okay, so here see, suppose this one is compressed region or this one is also peak. Okay, so time taken by this compressed region or density to complete one cycle. Okay, so here you can see, guys, if you transport this portion here to this portion again here, so what's becomes, this one is a one cycle. See this one. Okay, complete one cycle. Okay, so time taken by density of medium to complete one oscillation, okay, is known as time period of the wave. Okay, you can see this one is a pendulum. Now I leave it and again it come to same position, so it complete one oscillation. So how much time elapse to complete one oscillation is known as time period. Okay, now the next one is frequency. Okay, or its SI unit is second for time period. Okay, now frequency, so number of times complete oscillation takes place in medium in unit time is known as frequency of wave. Okay, so suppose for making one complete oscillation it takes time t, so frequency we denote if by v, then it is 1 by t, means this one is a 1 unit or divided by t, so its SI unit is hertz, or we write Hz, or you can write 1 by s in second, so s inverse. Okay, so guys, next one is a velocity of wave in medium. Okay, so suppose here lambda is distance. Okay, here for one cycle, and now for completing one cycle acceleration it takes time t, so what you will get here, velocity of wave or here sound. Okay, so you can say sir 1 by t is v, or this one is lambda. In some books you can see n lambda, means velocity equal to frequency into wavelength. Okay guys, now the wavelength, time period, frequency and velocity of wave in medium now clear to you. So based on what you read, we will see to numerical problem for your better understanding. Okay, see, so question guys, find wavelength of sound whose frequency is 660 Hz and velocity of sound in medium is 330 meter per second. Okay, so solution guys, here what you know, velocity of medium equal to v, or frequency into lambda, or you can say n lambda. Okay, v and n are both are same, which is frequency. Okay, now so what information are given in a question, the frequency is given and velocity of sound in medium is given, so we put here, so this one is 330 meter per second, or this one frequency 660 hertz. Okay, or this one is wavelength or lambda. Okay, so lambda equal to 330 meter per second here. Now this is 1 by 660 hertz. Okay, so hertz guys 1 by s. Okay, then what's happened here, 330 into, this is meter, this is second, this is 1, 660, again this is s. 1 by s, then s cancel out, or you can say also this is 1 by t. Okay, so 1 is a number or t is in second. 1 by s, which is frequency, which is frequency. Okay, now again this is 1 or this is 2, then 0.5 meter is wavelength of this sound wave. Okay, now see one more question. Guys, question is, a man threw a ball vertically down with velocity 19.6 meter per second and strike to water pond with velocity 58.8 meter per second. Find time when he will hear the splash of water. Okay, where g, acceleration due to gravity, is 9.8 meter per second square, and velocity of sound in air is 341 meter per second square. Okay, so solution guys, here this one is a tower, or here man is throwing a ball in down direction with initial velocity 19.6 meter per second. Okay, now this is filled with water, or this is pond. Okay, now when it strike here this water, then ball velocity, if we say v, is 58.8 meter per second. Okay, then when he will hear the splash of water. Okay, so guys, here the tower height is not given, we assume this is h here. Okay, so we need to calculate h. Okay, so first guys, we here calculate the time taken by ball to reach here to here. So this one is, suppose if t1, then we apply motion equations we have already discussed in our previous lectures. Okay, so v equal to u plus at. Okay, now v is final velocity, u is initial velocity. Here a becomes g, because here acceleration is due to earth gravitational force. Okay, so here v is given 58.8, u is given 19.6. again this one plus sign, because motion is down direction, or g is also down direction, because force due to gravity acting on ball is down direction. So this value is 9.8, then t becomes here guys 9. Okay, so this will come in this one, then negative like this one. Okay, or again you write like this one. Okay, so this will come this, so this is 1 or this is 4. so t equal to 4 second. Okay, now so what will be the height of this tower? So we apply here the motion formula, s equal to ut plus half at square. Here guys, u is 19.6, t is 4 second plus 1 by 2 or 9.8 into 4 into 4. So this is 1 or this is 2. Again we write like this one, or this 2 multiply 19.6 into 4. So again 19.6 into 4 into 2. Okay, so we will get finally guys 156.8 meter, which is height of the tower. Okay, now you in question the velocity of sound is given. So if we suppose the t2 time taken by this splash to reach here, then we write distance, or you can say displacement by time. Okay, as the motion is vertically down direction, so displacement and distance both are same. So 156.8 divided by 341. Okay, now after solving this one, you will get 0.45 or 98 second. Okay, so total time elapse. First the ball is coming down, again the sound wave is propagating through this air medium, so t1 plus t2. Okay, so initially 4 second plus 0.4598, then this becomes 4.4598 second. Okay, so when the man throw ball from here with velocity this one 19.6 and strike to water with this velocity, then total time elapse equal to 4.4598 second. Then he will hear the splash sound of water. So guys, in such way you can solve the numerical problem by applying the formula. Okay guys, if you think this lecture is informative for you and others, so please like and share this YouTube channel, Foundation JEE channel, to your friends and family, so they also get benefit from this channel. Guys, in next lecture we will discuss what is the unique property of sound, so that we can recognize individual voice, and also discuss the loudness, amplitude of sound, and reflection of sound, and what is reverberation. Okay, so those guys who did not yet on their YouTube notification, so please on your YouTube notification, so whenever I will upload the next lecture you will get the notification. So once again thank you for listening and watching this lecture. Have a nice day. Thank you very much.